All right, here's some data for our walking in the hallway lab that my students back at Southmore generated. And what we're going to do is make a simple graph with distance on the vertical axis and time on the horizontal axis. You have kind of some flexibility on how you do this. You can count by a variety of things. So it's just like in math class when we have an X, Y, T chart like this, and we have a system of a set of points basically, and you're just going to go through and plot the points on the graph over and up. Notice that T is in the position where X usually is, and X is in the position where Y usually is. So just don't get tripped up by that. You've got 4 sets of data, so I would say do each set in a different color or use like different symbols, ways that you can easily tell them apart from each other. And this is really important. Try to use the whole piece of graph paper the best you can. It's important to set your scale so that you don't have tiny little graphs, because we're going to be trying to look closely at the shape, and if the graph is too small, that's hard to do. Setting the scales is kind of up to you. My best advice, you're trying to make a linear scale where you count by some even amount each time. So I counted and I had 27 blocks going up and I had 36 blocks going over. And my highest data point for any motion was about 21 for time and was about 11 for distance. So I obviously have to go up to my highest point on each axis. And you just set your scale so that you use as much of the paper as possible. So I couldn't count by twos or by halves on this because I would have needed 44 blocks and I only had 36. So I just counted by ones. I could count by halves on this one though because I would have needed 24 blocks and I had 28. You may be tempted, well, maybe you could have counted by 1.5s or by things like that, but that's not a great idea, because if you're trying to estimate decimals and you've counted by something weird, that becomes really hard to do. So count by nice, easy to understand numbers, 1s, 2s, 4s, 5s, or halves, quarters, tenths. Don't count by like 17ths, because what is 0.63 if you're counting by 17? Anyway. So I'm going to graph my data for walking on this graph. We'll come back and take a look at it and try to interpret it. So here's my walking data. And as you can see, it looks pretty much like a line. It's not exactly like a line. If I bring this over, it doesn't line up perfectly for any point. But it looks like it's pointing somewhere. So what we're going to be trying to do is figure out what that means and whether we can use it to infer something about the motion. We're looking for a pattern. And although we only collected data in 3 points, and then we knew our 4th because we knew where we started, we're looking to see if there's a math function that can describe or estimate where you were for every point of time along this graph and maybe even a little bit beyond. So how do we do that? We ask ourselves, is there an overall pattern? And in this case, like I said, it looks pretty linear. So what we do is we go ahead and we take our ruler and we line it up so that we get about the same number of points above and below. So we're being kind of fair to each point. Obviously I can't draw this one-handed, so I'm going to draw my best fit line. Alright, so there's my overall pattern. This is called a best fit line. And we're basically saying that we think this line could help us predict where any other measurement we were going to take might end up. Now, one thing that's a little bit disturbing to some people is that not every one of our actual measured points is on this predicted line. That's okay. If you think about how we took this data it was individual kids standing a little bit less than, in this case, 4 meters, between 6 and 7, a little bit more than 10. And they were just starting and stopping a stopwatch. And maybe some of them stopped it too early. That would be the case of this guy here. Maybe someone stopped it too late. That would be the case of that guy there. That's going to introduce error. So we want to ignore small random differences that don't really suggest an overall pattern. Now, what do I mean by small random differences? It's very hard to tell from this graph because we had such a small amount of data, only 3 points, and we used it to predict for so very many times. So for better labs, it would be better if we had more data points. The problem is the more data points we'd have, the more timers we'd have to have, the more ways we'd have to have of collecting data. And that would be hard if each kid is just sitting with a stopwatch. We'd have to find some way to do it automatically. So I'm going to stop this and I'm going to graph the other data, and we're going to see if it tells us anything. So here's our completed graphs, and there's some interesting patterns here. The first was they were all fairly linear, although crawling particularly, but also crab walking, we had some points that were pretty far off the line. So whether that's linear or not, or whether there was just a lot of error in those measurements, it's hard to tell. So I did a best fit line there. We'll assume they were linear, but it would be nice if we had some more points between them to make us feel a little more certain. There's a big overarching pattern on these graphs, and if you look at what they mean, the red one was running, then walking, then crawling and crab walking. Running was the steepest, crab walking and crawling were the shallowest. And if you think about that, the difference between them is that this is fast, these are slow, and that guy's kind of in between. So the slope of the line must have something to do with speed. In fact, it is. If we write a kind of customized slope-intercept form, y equals mx plus b, for this graph where x is where y is supposed to be and t is where x is supposed to be, the slope actually ends up corresponding to how fast you went. So I put v for velocity there. The intercept xo, that's where you were when time started. In all of our cases, it was 0. And all xo means in physics is your position originally, the place you started. So this equation here is just the y equals mx plus b thing you know from math class. And it tells us where you are at every time. Assuming, of course, you're moving on these lines. So what we're going to do is we're going to get the equation for each of these lines. That'll help us predict where we are at any time, and it will allow us to calculate the speed of each of these objects. There's only one caveat, and that is we want the slope of the line. And to do that, we have to pick 2 points. Now, it's kind of tempting to pick the data points, which we know from our data table. Those are real places that we were. But as you can see, they're not on the line. So we actually don't want to pick them. Now, it seems a little bit backwards. But if you got the slope between these 2 points, you wouldn't be getting this black line. You'd be getting a line that connects the two. And what we're saying when we draw this line is that our best guess is that we had a linear pattern and that this guy stopped his watch too fast and this guy up here stopped their watch too slow. And they kind of averaged each other out, and we split the difference between them when we drew our line. So once you've drawn your line, you don't want to use data points because each of them has the errors from an individual person. You just want to use the slope of the line you drew. So how do you do that? Well, you just find some points that are easy to guess. This one kind of goes through the crosshairs, and so does that one. We just find out what their ordered pairs are. That guy is 17, 10. And this guy is 10, 6. And then we're going to plug them into the slope equation to get each velocity. we'll use this form of it. So I'm not going to sit there and make you watch me calculate all my slopes, but we'll come back and visit after that, and we'll move on to our next lab. All right, so here's my finished data analysis. I got the slope for each of these lines using the slope formula, and then I plugged that in to the original equation, and since the intercept was 0, my equations all look pretty similar. X was equal to the slope times t plus 0. And as we saw, running had the steepest slope of 2.25. Crab walking had the shallowest slope of 0.45. Notice I put a unit on each of these values. I didn't put the units here because it would take up room and make it look messy. But don't forget that everything measured on the x-axis is in seconds, and everything measured on the y-axis is in meters. So when you do rise over run, the units have to stay there too. So rise is measured in meters, run is measured in seconds. We end up with this unit of meters per second. And that's the unit for speed. Meters is a distance, kind of like miles. Seconds is a time, kind of like hours. So meters per second is kind of like miles per hour. It's a speed. So this is our data for this lab. We learned a couple of big things. We learned an equation that describes the motion of people in these various activities. We learned that it's just comes from the slope-intercept form of a line. And we learned that the slope of the line equals speed, since running the fastest gave us the steepest slope, and crab walking the slowest gave us the shallowest slope.